All right, let's get started with lecture 3. So last time we pushed this discussion of the wave-particle duality. We talked about the double-slit experiment for electrons, and basically the result was that if you shoot electrons through two holes on a screen, they basically hit the screen at places that appear random. But after a while, when many of these measurements accumulate, you get lots of bright spots where electrons hit the screen. They show this pattern that has kind of bright fringes and dark fringes. So the idea was that perhaps there is something that has a wave-like character. So we call that the wave function. Let's say for a one-dimensional system, it's just psi of x, or if, like in the case of those electrons in 2D, it could be x and y on that screen. Or in general, in three-dimensional world, it could be a function of x, y, and z position in the three-dimensional world. And of course, this is a wave function that can and does change as a function of time. And what we talked about was the interpretation that absolute value psi squared dx is the probability of finding the particle in an interval x and x plus dx. So in a tiny interval of length dx located at point x. So this psi x absolute value squared is something called the probability density. Basically, if you multiply it by an infinitesimal length in one dimension, area in 2 dimensions, or volume in 3 dimensions, it gives you the probability of being or finding the particle in that tiny region of space. We did a couple of examples just in the one-dimensional case, gaining some experience with this psi squared. So one thing I want to start talking about today is kind of finding quantum averages, also known as expectation values. So basically, like, suppose you measure a position, right? So suppose these electrons hit, and most of the time they hit over here, sometimes they hit over there, maybe more hit over here. So maybe that's some kind of a pattern that emerges after an experiment. So maybe then the corresponding psi x squared, if you wish, has a peak around here in this region. And maybe it decays and has a smaller peak in that region, for example. And basically now, suppose you have a list of positions, right? For each of these points, you have x1 up to xn. So one natural question is, what is the average, right? And if you take the average, well, it's going to be somewhere around here, right? It's not going to be halfway because you have more weight over there, so more particles hit here. So kind of finding averages from probability densities is a standard problem in probability. So it's kind of helpful to start with a discrete example. So here we have a continuous case. Basically, the particles can hit anywhere, so the position can be any real number. And then we can only talk about the probability of being in an infinitesimal interval, and that probability is proportional to the length of the interval. When the length goes to 0, the probability goes to 0. So we really talk about probability density here. But in the discrete case, suppose, you're dealing with a quantity that's not a real number, maybe it's an integer. So, for example, suppose you're thinking about the age of students in a class, just rounded up or down to a year. Like you give your age as an integer, you're 20-year-old or 21 years old or whatever, right? So let's think about an example regarding discrete variables and probabilities. So I don't know, take a class and let's say you have different ages of students and then you have number of students with a given age. So I don't know, we have maybe a class of 20. So let's take a larger class. Let's say, I don't know, 10 students are 20, 15 are 21, 16 are 22, 8 are 23, for example. So I kind of didn't write it correctly. So let me fix this. So here we're saying this is number of students. Here is their age. Okay. So let's give it some numbers. So age we call, for example, J, right? So this is J equal 20, J equal 21. And number of students with a given age, let's call it NJ, N sub J. Okay? So first, given this, if I ask you what is the probability that someone is 21, well, you're going to just divide the number of students who are 21 by the total number of students, and that's the probability of, if you pick a random student from this class without any consideration, that's the odds of the student being 21. So P of J, the probability of age J, is going to be NJ by the total number of students. Let's call that N. And N is, of course, in this case, is 10 plus 15 plus 16 plus 8. So it's going to be sum over J of NJ, right? It's a sum over all possible ages of the number of students with that age. That's the total number of students you have. Okay. Now, if I want to find the average, let's say, let's call it, I put J in brackets like this. So that's the average age of the students. Well, I have, in this example, what do I have? So I have, if I just add all the ages and divide by the number of students, well, I have 10 students who are 20, so I get 10 20s, right? That's 10 times 20, plus 15 times 21, plus 16 times 22, plus 8 times 23, divided by the total number of students. That's this thing, this numerator is a sum of all the ages, right? Where you're summing over students, and then divide it by 10 plus 15 plus 16 plus 8. So mathematically, in this notation, that's going to be sum over j times nj, right? J is the age, these numbers 20, 21, 22, 23. Nj is the number of folks who have that age. And then we divide it by n, which is also the number of students, which is a sum over j and j. All right, but notice from this probability, I can write this as 10 times 20 divided by that number. So this number is what? 15 plus 16 is 31. 31 plus 10 is 41 plus 8 is 49, it seems. Okay. So I can write this alternatively as 10 times 20 divided by 49, right? Plus 15 times 21 divided by 49 plus 16 times 22 divided by 49 plus 8 times 23 divided by 49. And then 10 over 49 is the probability of being 20 years old. 15 over 49 is the probability of being 21 years old, etc. So in the same way, I can write this as sum over j, and then I take this inside, so I divide every term in that sum by this denominator, that's nj over n, which is the probability of being j years old. So that's sum over j, p, j. So if you have a list of discrete numbers, these are some random variables, they have different probabilities. And if you want to find kind of the average j, that's the recipe. We just sum over all of them and we multiply each by its probability. Notice one thing that's kind of obvious, right? The probability of having a certain age is always 1. I mean, the sum over probability of all possible ages is 1, right? So that simply follows from this definition if you think about this discrete case. So it's worth noting that, as a side remark, sum over j p of j becomes sum over j nj over n. I factor out this n, so it's 1 over n sum over j and j. And this is just capital N, so it's n over n, it's 1. That's the statement that, everybody has some age, right? So if you have a group of people, and if they have different probabilities, the sum of all possible probabilities should be 100%. In the same way that we talked about the normalization of the wave function, we said the particle is somewhere, right? So if the probability of the particle being in this tiny interval is psi x squared dx, then an integral from x minus infinity to plus infinity of that quantity is 1. So going over here in the discrete case, we say the average of j is sum over j times pj, and of course 1 is equal to sum over j pj, sum of all probabilities. So now we are ready to kind of use this result for a discrete example to write results for the continuous case. So going back to our particle on the real axis, right, we have a continuous line and we imagine these tiny intervals of length dx. So basically, like, we can treat each of these tiny intervals as some kind of a discrete thing. So then then these carry over. So the analog of sum of all probabilities being 1 becomes 1 is equal to integral from minus infinity to infinity of those tiny probabilities. So that's psi x squared dx. All right, this is one probability for one tiny interval, and the integral as these infinitesimal quantities. Now we can define or write an expression for the average x, right? Expectation value of position. Basically, inside this sum, we just multiply each probability by the value of x. So let's say to each of these intervals, they're at position x. If the interval is really tiny, we can pick its middle and say that that's where it is. So that's going to be given by integral minus infinity to infinity of x times psi x squared dx. Right, so this is kind of the analog, the continuous analog of p of j, and this x is the continuous analog of j. So that's a typical problem, like you're given a wave function and you want to find the expectation value of position given that wave function. Well, it's just an integral over x, and then we multiply x by the probability density psi x squared. So last time I think we did an example where we had a wave function, I believe, that looked like a triangle. So I think here we had 0, here we had small a, and then it went up to some finite value, right? At a over 2. So that was our psi of x as a function of x. And it was 0 everywhere else. So this value we calculated from requiring that the wave function is normalized. So I can take a minute and look it up. So basically what we found was if it's a times x for x less than a over 2 and larger than 0, and it's a times a minus x for x between a over 2 and a, and 0 otherwise, we found from requiring that integral minus infinity to infinity of psi x squared dx is 1, we found this capital A must be square root of 12 over a cubed. Okay, so now suppose I want to calculate the expectation value of x. What is average x given that wave function? Well, if you think about the probability distribution, it's going to look something like this, right? It'll look like that, like this, I think. Again, here we have a 0, a over 2. So that's squaring that thing. So the linear curve becomes kind of like a quadratic parabolic curve. So already without doing any calculation, right, we see that this distribution is symmetric around a over 2. So once you're doing the average, basically for any interval that's like, some distance, let's say x to the left of this symmetry line, there's going to be a tiny interval that's the same distance to the right, and you have the same probability. So very intuitively, like if you have a probability distribution that's symmetrical line around some line, you expect the average of position to be on the line, right? If you take the average of x for this and that, they have the same probability, right? It's symmetric, so they have the same height. And the average of these two values, let's say a over 2 minus x and a over 2 plus x, is a over 2, right? So that's what we expect without doing any integral. And it's kind of, maybe it's instructive to actually do the integral. That's kind of the hard way, but just to verify that this a that we found before from this also works. So let's do that. Let's do a brute force calculation of average x for this particular wave function. Okay? So what should I do? Well, it's integral from minus infinity to infinity of psi x squared x times dx, right? Okay, so this is going to be integral from 0 to a over 2 of the wave function in this region squared, so that's a squared x squared times x times dx, plus integral from a over 2 to a of this one times x dx. And we know that a squared is 12 over small a cubed, so I factor it out. So 12 over small a cubed, 0 a over 2 x cubed dx plus a over 2 to a. Let's just expand that out. So a minus x squared becomes a squared minus 2ax plus x squared times x dx. So that's 12 over a cubed. X cubed integral is x to the 4th over 4. So that's going to be a over 2 to the 4th over 4. Plus, doing this integral, a squared x integral is x squared over 2. We have minus 2ax squared, so it's going to be minus 2ax cubed over 3. And then we have plus the integral of x cubed, which is plus x to the 4th over 4. And this runs from a over 2 to a. So here this ran from a over 2, from 0 to a over 2, so I didn't bother writing the 0. So that's 2 to the 4th is 16. 64. Let's see. So that's a squared minus a over 2 squared, which is a squared over 4. Let me a squared here. Let me correct this here. Then we have minus 2a over 3, a cubed minus a over 2 cubed. So a over 2 cubed is a cubed over 8, right? 2 cubed is 8. And finally, I have a quarter a to the fourth minus a over 2 to the fourth, which is a to the fourth over 16, right? 2 to the fourth is 16. So that should be our answer. So see, all of these terms have an a to the fourth, right? A squared times a squared, a times a cubed, a to the fourth. And I can factor out that a to the fourth divided by a cubed, get a. So that's good. I'm finding the average of position, which should have units of length. A is a length. So yeah, it's good that we're getting, that's a sanity check. We're getting a times a dimensionless number. So let's factor out that a. And then we have a factor of 12 outside, so let me write it as 12a. And let's see what's left inside. So I forget about all these a to the fourth factors. I factored them out and divided by a cubed, so I'm left with an a. So I have 1 over 64 plus 1 over 2 minus 1 over 2 times 8, which is, 2 times 4, which is 8. Minus 2/3 plus 2 over 24. 3 times 8 is 24. Plus 1 over 4 minus 1 over 64, right? 4 times 16. So 12a. 1 over 64, 1 over 64 cancel out. Can take a common denominator here. That's going to be 24, it seems. So 1 over 2 is 12 over 24. 1 over 8 is 3 over 24. This is minus 16 over 24 plus 2 over 24. Plus 6 over 24. All right, so I factor out the 1 over 24, so I'm going to get 12 over 24, which is a half. So that's a over 2. Then I have 12 minus 3 minus 16 plus 2 plus 6. So 12 minus 3 is 9, minus 16 is minus 7, plus 2 is minus 5, plus 6 is 1. Good. So that's a over 2. As expected. Again, this was a really ridiculous way of doing this, right? It was very brute force. But it's sometimes good that if you don't find like clever ways, you see that the brute force can work as well. But in general, yeah, if you have a kind of an axis of symmetry, then the average of position is going to be on that symmetry axis, as we gave an argument before. All right, so now I want to go back a little bit, and I want to discuss kind of what would be the equation that governs the behavior of this wave function. So we want to introduce something known as the Schrodinger equation, which is a fundamental law of nature. And tells us, it's a differential equation that tells us how this wave function behaves. So to motivate it a little bit, let's go back to the Broglie relationships, and we try to start with a free particle, kind of guess a wave function for a free particle. Let's say a particle with momentum p moving, for example, moving to the right, for example. And then what we want to do is to kind of guess an equation for which this is a solution. So the Schrodinger equation is, of course, a fundamental law of nature. There's no way to derive it. It's something that was guessed, but I just don't want to write it as I hear that's a law of nature. It's sometimes helpful to motivate this and put it in the context. So for a free particle, let's review a few things. So consider a free particle of momentum p. Okay, so first we know its kinetic energy, E, is going to be, let's say, it's 1/2 mv squared, right? And v is p over m. So it's going to be p squared over 2m. Okay, so I have a free particle, it has momentum p. Classically, it has this kinetic energy. And if you think about the Broglie relationships, we know that associated to this momentum and energy, there are wavelength and a frequency. So we have lambda is h over p, and we have the frequency is e over h, which is p squared over 2mh. Again, oops, why did it go? Right. Okay, so now if I want to write a sinusoidal plane wave, remember the Euler equations, we had sines and cosines. Alternatively, we could use e to the I theta and e to the minus I theta. Just to remind you, Euler equations, we had e to the I theta was cosine theta plus I sine theta, and e to the minus I theta is cosine theta minus I sine theta. It's just putting minus theta in the equation above. Cosine of minus theta is cosine theta. Sine of minus theta is minus sine theta. So sines and cosines, serve as one way of writing plane sinusoidal waves. These guys are linear combinations. Again, they're valid ways of writing sinusoidal plane waves. Okay, so make sure we can just invert this and write, for example, if I add these, I get 2 cosine is e to the I theta plus e to the minus I theta. So cosine theta over 2, and if you subtract these, sine theta becomes e to the I theta minus e to the minus I theta over 2i. Alright, so I guess, let's say for free particle matter wave is, for example, this, right? Is something like psi of x and t is equal to some normalization constant e to the I remember the phase of a sinusoidal wave that we looked at in 163 was something like kx minus omega t, right? Something like this. So that's quite a reasonable guess. And k and omega were related to wavelength and frequency. So remember, k was 2 pi over lambda. Omega is 2 pi f. So if I insert these expressions for the Broglie wavelength and the Broglie frequency into this, a good guess for the free particle matter wave would be something like this. And then this is 2 pi over lambda. Lambda is h over p, so it becomes 2 pi over h times p, and then that multiplies x, so this entire thing is k, minus 2 pi f, right? Omega is 2 pi f, and f is p squared over 2mh times t. Okay, so that seems like a reasonable guess for a matter wave. And now something interesting happens here. So if I kind of want to derive an equation that governs the dynamics of this, we see that it's an exponential, and there's something proportional to p multiplying x, and something proportional to p squared multiplying t. So this motivates, if I basically take one derivative with respect to time, I'm going to get like something that looks like p squared times some stuff times this exponential. If I take the derivative with respect to x, with respect to position twice, every time I get a factor of something times p, so again it's going to be, if I take it twice, I get something times p squared times that exponential. So if this is a solution to a linear differential equation, linear in the sense that there are no higher powers of psi, it's only psi and then some derivatives, for example, act on it, which are the types of equation that satisfy like the superposition principle. So if you have one solution, if you have two solutions, a linear combination of those two will also be a solution. And that's appropriate for wave phenomena, then maybe that's a good equation. So let's try to see what happens. So if I take, for example, the derivative with respect to time of that expression, well, I get a factor of, remember, the derivative of e to the alpha with respect to alpha is just e to the alpha, right? So if I use the chain rule, it's just this thing. So it's minus 2 pi I p squared over 2mh. That's the coefficient of t in the argument of the exponential times psi of x and t. The derivative with respect to t of psi, of course, of psi of x and t. So let's fix this here. Of psi is equal to that. Okay, so let's now do this slowly. I want to take one derivative with respect to x becomes the coefficient of x in the argument of the exponential is 2 pi I p over h. I bring that down, and then what remains is the rest. Now if I take another derivative, the second derivative of this expression with respect to position, I get one more of these factors. So it's going to be 2 pi I p over h quantity squared times psi. So that's kind of interesting. Let's write it. It's going to be, one thing I'm going to do, I'll define, and it's a very standard notation. H bar is just defined as h over 2 pi. So it just simplifies the notation. So this, is going to be I squared, which is -1, p squared, and this is h over 2 pi, it's like over h bar, so I'm going to get h bar squared times psi, second derivative. Here, the first derivative, this is minus I have p squared over 2m here. I have I over h bar, right? This is minus, this is I. 2 pi over h is 1 over h bar. And then p squared over 2m remains, and that multiplies psi. So, so what is happening? So I can basically relate these, right? So what I have is, if you consider p squared over 2m times psi, so let me take that quantity. So I can write is equal to minus h bar over I times the first derivative of psi with respect to t. But it can also be written as from here, it's going to be minus h bar squared, right? You multiply both sides of this equation by h bar squared and divide by 2m. Second derivative of psi with respect to position. So the equation that governs this free particle that doesn't experience any potential, any forces, it has a constant fixed momentum, is going to be I can manipulate this a little bit and write, so 1 over minus I is I, so it's going to be I h bar, right, because I squared is -1. So this -1 in the numerator is I squared, and then you divide by that I. Derivative with respect to time of the wave function is here I have to, of course, divide by 2m, right? This is p squared over 2m. That's just p squared. Is minus h bar squared over 2m, second derivative of the wave function with respect to position. So the genius of Schrodinger was saying, well, when this thing minus h bar squared over 2m times the second derivative acts on psi, it gives you p squared over 2m. It's like the kinetic energy. So let's think of that as an operator, something that acts on the wave function. And the way he guessed the general Schrodinger equation was, well, if you have some potential acting on the particle, then the total energy is the kinetic energy plus the potential energy. So maybe just the time derivative is governed. Maybe on this side, this just remains general potential. what Schrodinger equation wrote down was something like this. Is minus h bar squared over 2m second derivative with respect to position plus the potential as a function of x acting on the wave function. And that's a celebrated Schrodinger equation. It ties in with our understanding of plane waves, of sinusoidal waves, and of the Broglie relationships. And there's this really key insight that there are operators associated with different quantities. So there's some operator associated with energy. And for kinetic energy, the thing that acts on a wave function of a free particle whose kinetic energy is constant, whose momentum is constant, is that. Minus h bar squared over 2m times the second derivative. So if you want to write a more general equation, this seems like a reasonable guess. So this is the fundamental equation in quantum mechanics. It's really the analog of Newton's second law, right? So when you're talking about the Newton's second law, well, there you have like a deterministic picture that the particle has a given position at a given time, and then the forces acting on the particle, again, they're related to some potential, right? So minus some derivative of a potential with respect to position is a force. And second Newton's law basically tells us, what the acceleration is. So it tells us something about how the position is changing in the presence of some forces. And Schrodinger equation does the same thing, except we have a very different interpretation, right? So we have this mathematical object known as the wave function, whose property is that when you take its absolute value and you square it, you find the probability density of finding the particle at various random places. But then again, like if there's some potential acting on a particle of mass m, suppose you have an electron going around the nucleus in an atom, right? There's going to be some electromagnetic interaction, so there's some potential electric energy, like minus e squared over the distance between the electron and the nucleus from the Coulomb force. So that enters the Schrodinger equation. That's the potential that's affecting the dynamics of this object, and the Schrodinger equation tells us how the wave function is changing as a function of time. It relates the time derivative of the wave function to the energy operator, to this thing. Remember, this part is like the kinetic energy. It's an operator associated with the kinetic energy. This is the potential energy. And it's a linear differential equation that tells us how the wave function would change. All right, so this is known as the time-dependent Schrodinger equation. So I want to emphasize that this was not a derivation of the Schrodinger equation. This equation is a fundamental law of nature, like Maxwell's equations of electromagnetism, or Einstein's equations of gravitation, or whatever, or Newton's law. So it's not something that we derive from some first principles. Basically, the arguments we went through, kind of making use of the Broglie wavelength, writing some plane wave, and saying, oh, what is a linear differential equation that this satisfies if there's no potential, and then taking a guess of where the potential should be placed. I mean, this is just the process of discovering something fundamental that cannot be derived. So this equation is really one of the postulates, one of the fundamental laws of nature in quantum mechanics. And the interpretation is really the analog of Newton's law. Basically, in quantum mechanics, the description of particles is in terms of this mathematical thing called the wave function, which when you square it, you learn about the probability of finding the particle somewhere. And then how the wave function changes, well, it has to do with, let's say, the forces that act on the particle, right? It's very much kind of like classical mechanics. And of course, the forces are in turn related to the potential landscape in which you place the particle. All right, so I think this is a good place to stop, and we'll continue the discussion next time.